Hello and welcome back. In this lesson, we are going to look at the concept of spanning a space. And what we are going to think about is if we have a whole bunch of arrows in space, then can we combine these arrows in some way to get us a resultant net arrow pointing in a specific direction? And can we then extrapolate this to saying that if we have a 2D space, then can we create a vector or can we create an arrow in any position in this 2D space? So the idea is depending on the dimensions of the space we are talking about. So let's say if we are talking about a 2D space, then we are going to ask a question: how many of these vectors do we need to be able to create our resultant vector that we talked about? And uh, and then how does that work? So that was very general sort of thinking about it. Now we'll try and attach some specific names to each of these. When we say that we are going to combine uh, mix and match vectors, then add or multiply them together to get a resultant vector. Usually, the idea is that there is a minimum number of such vectors that we can, for a particular space, that we can combine to get any resultant vector in that space. So that minimum number is usually dependent on the dimensions. So if we have a 1D space, then we just need one such vector. If we have a 2D space, then we need two such vectors. We have 3D space, then we need three vectors. And probably wondering, how do these vectors that we talk about look like and what are they called? So there is a general term for describing these sets of vectors, and that is called as basis vectors. For example, if we look at the 1D case right here, we can say that our basis vector set S looks like something like this one. So this is just a arrow pointing along the x-axis. So let's say that's x is equal to 1, and that's the arrow we are pointing in the x-axis direction. It's just 1D space. Now with just one vector, it's difficult for us to sort of gain or create a vector in the rest of the space, because we are talking about 1D space. What the best that vector that we have, the basis vector that we have, can do is we can multiply it with some scalar to maybe move along that same straight line. So we could maybe get points along that line that we have, also in the negative direction. What happens if we talk about 2D space? In 2D space, let's say our set of basis vectors is this. This is our vector. This is one vector, and then we have a second vector that looks like this. Now, if we try and plot this on here, we see that this 1 0 would look something along the x-axis, which would be like this, and then 0 1 vector would look something like this along the y-axis. So the idea here is that if we combine these two vectors in different ways, we should technically be able to uh, create or get any vector in this entire 2D space. And so the key idea here is how many such vectors we need. Because we are in 2D space, we need 2 such vectors. Here we were in 1D space, so we needed one such vector. And this can go on to 3D space as well. So in case of a 3D space, maybe our set of vectors, the basis vectors, could be as follows. Maybe there's one vector that's along x-axis, there's another vector that's along the y-axis, there's another third vector along the z-axis. And what that suggests is that if we have a 3D space where we have x, y, and z, and these vectors that we just wrote, which is one along the x-axis, one along the y-axis, and one along the z-axis or z-axis, these can be combined to technically reach out to any uh, dot or point in the 3D space. And that is to say that we can create any vector based on these sets of three vectors by maybe multiplying them or putting them in some combination. And the way that combination works is we could say that uh, that space we are talking about is equal to this is x1 times u1, and that could be our vector 1 plus x2 times times u2, and that can go on until xn times u of n. So as many number of vectors as there are dimensions, and so the u is essentially referring to these basis set of vectors in this basis set. So if we have a 2D case, then we just have u1, u2, and this would then be u1, this would be u2. Now, as we are talking about general vector space, we can also think about something called as a polynomial space of, let's say, here is of degree 2. So this is what we are saying is a space of polynomial up to degree 2, and there can be a set of basis vectors for this space as well, which we could represent as something like 1 t square, and the polynomial that we are talking about could be a0 plus a1t plus t square. And the idea here is that we can again use this set of basis vectors in polynomial space to create any other polynomial that is in that particular space. And this can be written as p of t is equal to a0 plus a1t plus t square. Now, with that in mind, let's dive into some of the examples that will hopefully make these concepts more clear. Let's now look at a 1D case, and here let's say our set of basis vector, or which is just one vector in it, is denoted by this 1. So if we were to look at the linear combinations of this vector, it's just going to be a times a, and that's 1 represented as a vector here, which is just going to be a. Now remember, when I say linear combinations, that's the whole point of the basis vectors. The idea is that if we combine these vectors in some form which is linear, let's say x1 times u1 plus x2 times u2 plus dash 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 plus like this xn times u of n, then we can get any resultant vector. So that's the whole linear combination. That's what we are talking about. And in this explanation, we might switch these notations just a bit. We So we'll say this is, let's say, a times the vector here u1 and so on. So now if we try and um, use any number for a, we can get any point on that line. So if we think about our plot where we have this x-axis right here, and the vector that we have is a, and let's say the value of a is 1, then we see that we can reach that point of 1. If a value is 3, then we could reach the point 3 on that line. So that's the idea. So what we say here is that the span of this set of basis vectors S is the entire number line, which we can denote by r to the power 1. In 2D case, we can again think of the basis vector. It could have just one vector, for instance, as we see here, 1 1. And now if we try to create a linear combinations of this, we would do the following. We would say a, and this is then the vector 1 1, which we can think of it as this vector 1 1, and if we multiply a here, we are essentially creating a vector, which we can write in the form parenthesis a comma a. And here then we can say that for any given value of a, so let's say a is 1, then our the vector that we can reach is 1 1. If we say that the value of a is 2, then we can reach the vector 2 2. If the value of a is minus 3, then we can reach the vector minus 3 minus 3. So essentially then what the span is for this set of basis vector, that is what vectors it can reach, is along that line y is equal to s. So we can say that the span is all points on the diagonal line y is equal to x. And y diagonal, if we try to plot this, if we have 1 1 like this, it's going to be this point, 2 2 is going to be this point, 3 3 is going to be this point, and so that line would stretch something like this: 1 2 3 1 2 3, and likewise on the negative side as well, -1 -2 -3 and so on. So that was the second example where we looked at a 2D case with just one basis vector. Likewise, in 2D case we can have two basis vectors. So let's say the first one is 1 0 and the second vector is uh, 0 1. Now with this set, let's try and create the linear combinations of this. So linear combinations, and we would say a times 1 0 plus b times 0 1, and that gets us the resultant vector ab. And here a is 1 0, so we can write it like this. B is 0 1 like this, and so if we try to multiply this, we get a0, and then we get 0b, and so this essentially is nothing but a b, and that's what we wrote here, which is in the vector form ab. and as we can plug in some numbers now, if you try on some values, let's say a is 1, b is 0, then the resultant uh, vector that we get here is 1 1, so we can reach this vector 1 0. And how do we get that resultant vector 1 0? Well, we just have the values 1 0 plugged in there. If we have a value of a which is 0, value of b is 1, then we can reach the vector 0 1, and so on. If we have a completely different values, a is equal to 3, b is equal to 2, then we can reach the vector 3 comma 2, and so on. The a can also, let's say these can have negative values, so a is -1, b is +4, then we can reach the vector -1 4. And so what we can say is that uh, the span, this case span of S is all the points in the space R2, that is the entire 2D space can be reached by using this set of basis vectors. And the question you probably have now is, hey, why do you have just 1 0 or 0 1? Why is it that simple? Can we have some different numbers there uh, as basis vectors that can be used to create or reach any point in that particular space? And the answer is yes. Yes, and the criteria that is there is they have to be linearly independent, as we saw in the previous video. As long as these as long as the vectors that we have in the set are linearly independent, they can um, be used as basis vectors. And what we mean by basis vectors is we can combine them in a linear combination to reach any point in that space. If we have a 2D set of basis vectors, we can reach any point in the 2D space. Just like that, if we have a set of three vectors, let's say it can be 3D space. So let's say we have these vectors. S is equal to 1 0 0 0 1 0 0 0 1, then we can create a linear combination of this linear combination, and this would be a times 1 0 0 plus b times 0 1 0 plus c times 0 0 1. That essentially is a 0 0 plus 0 b 0 plus 0 0 c, and that is a b c, which is essentially a comma b comma c. And so with ABC, with any values for ABC, we can get any points in the 3D space this time. So if we have x, y, and z with the values that we have here in the 3D space, we can uh, using the combination of these three vectors, we can essentially get any point in the 3D space. And so from the span, we can say that the span of S is the entire 3D space denoted here by r raised to power 3. And therefore, to summarize this, here is the snapshot. So span of the set 1 is simply a line, and the dimension is 1D. The span of 1 comma 1 is again a line, but this is in 2D, and the dimension is still 1 because there's no room for it to move around except that line. And then if we have a set of basis vectors, let's say 1 0 0 1, then this can span the entire plane. It can find any point in the 2D plane, and so the dimension here is going to be 2D. Likewise, if we have a span, if we have a basis set of basis vectors which has these values, uh, 1 0 0 0 1 0 and 0 0 1, then this can span the entire 3D space. So it can span the entire 3D space, and therefore the dimension is also 3 in this case. So the basis vector then is simply a smallest set of independent vectors that can that cover the space they are in. And for this, the space is entire 3D space denoted by r to the power 3. This is denoted by r to the power 2, and for this one we are denoting it by r to the power 1. So that's the general idea about the basis vectors. We'll now look at some specific examples. Let's look at the plots here in Desmos, and what we can see is two arrows, red arrows, and the one arrow shown here in black. These two are the basis vectors we are talking about, and in this case, this arrow right here is denoted by this vector that starts at 0 0, goes up to 1 1. So that 1 0. So that's the 1 0 vector, and this is the 0 1 vector that we just talked about. And using these two vectors, we can create this vector or reach this point 2 3 on the 2D plane. We can reach the same point 2 3 using another set of basis vectors shown here by the blue dotted lines. And that's the beauty of basis vectors. It's not that the basis vectors have to be simple 1 0 0 1. They can be any value, as you can see in this case. These two can be combined linearly to get the same vector. Now the catch is, or the point to note here is, that the coefficients in the linear combinations would be different in the case of blue set of basis vector as opposed to the standard basis vector shown here in red. We could also have these vectors, which is a scaled up version of the basis vectors, standard basis vectors 1 0 0 1. Instead we have 0 2 2 0 as the basis vectors, which we can again combine to get our output or resultant vector 2 3, or in other words we can say that we can reach that point 2 3 in the 2D plane, and we can show that mathematically. Let's start out with the simple case where we have the standard set of basis vectors, where we say S is simply equal to 1 0, and then we have 0 1. Here, as we just saw, to we just saw that the final values that we get are just a b, and so here if we set the value of, if a is equal to 2 and b is equal to 3, then of course we can get to the point 2 3. Now if we have a basis set that is a little different, let's say we have 1 1 1 minus 1, then how do we get to that point? So this xy in this case is going to be equal to 8 times this 1 1, and let's say b times 1 minus 1. Note that when I say xy, I'm essentially thinking in this vector xy, and so here we get a plus in square brackets we have b and then minus b. So here what we have are two equations. So x y is equal to a plus b, that's the first equation. Then we have a minus b, that's the second one. We can write them out as x is equal to a plus b, and then we have y is equal to a minus b, and we can add these simultaneous equations. These cancels out, and so what we get is x plus y is equal to 2 times a. Therefore a is equal to x plus y divided by 2. So that's the first case. That's the way we can get the value of a, and then likewise we can plug this value of a up here in any one of these equations. Let's say we use the top equation. So x is equal to x plus y, and then divided by 2 plus b, and so we need the value for b. So here is what we'll do. We'll say b is equal to, um, we sort of bring all of this to the other side, so that's going to be x minus x plus y by 2, because we moved it to the other direction, and so this becomes 2 times x minus y divided by 2, and so we end up with the value of b equals to x minus y divided by 2. That's how we can get the values for a and b. Now given that we are interested in trying to find the this point, we know that we want to reach there, so we can try and get what values we need for a and b to get to that point. So in this case, this is our x, that's our y, so we can say 2 plus 3 divided by 2, that's 5 by 2, that gets us 2.5. And likewise for b, it is x minus y divided by 2, and that's minus 1 divided by 2, and so we get minus 0.5. And so the linear combination that we are talking about, to reach to the point uh, 2 3, that's the point we are trying to get to, would have to be as follows. It would have to be 2.5 times the first basis vector 1 1, and then plus minus 0.5 times the second basis vector that we have is 1 minus 1, and so that will get us the value of this, that will get us this value 2 3. And we can check that if we would get that value by simply performing this calculation, where we just uh, do this multiplication, minus 0.5 times 1 minus 1, and so this simply becomes 2.5, 2.5, and this becomes plus, we have this is minus 0.5, minus minus plus 0.5, and so when we add this 2.5 minus 0.5 gets us value of 2, 2.5 plus 0.5 gets us a value of 3, and that is exactly what we were trying to reach, is the vector 2 3 in the 2D space, uh, using the linear combination of basis vectors, which we have here. The What was different as compared to this set of basis vectors are the values of a and b. So earlier case, the values of a and b were 2 and 3, and this time the values of a and b were 2.5 and minus 0.5 to reach the same vector 2 3, and we already see that in here. And likewise, if you try and calculate for the set of basis vectors 2 3, this 2 0 and 2 3, sorry, 2 0 2 and 2 3, 2 0, to get to 2 3, you'll get a different set of values for a and b. Now along those same lines, if we try and think about spanning the entire space, here is an example of that. What I have are two vectors. One is denoted by 0 a0, other one is denoted by a b, and we have the values of a and b that we can change. So if we fix the value of a to, let's say, +1, and we vary the values of b, we see that it can reach any point in that space. Likewise, we can go in the negative direction, and as you can see, we can reach any point in that space. Likewise, we could fix the value of b and we could reach any point in that direction. So that's a very simple demo to show how we can uh, reach any point here. Of course, I'm not showing the basis vector calculations, but uh, just showing that uh, varying one value in here can allow us to get to any point in this space. Now let's shift gears and look at polynomial space. In the polynomial space, let's say this is what we have, which we said earlier it can be denoted by p to the power 2, is this. And here, let's say the basis vectors we have are the following. We can write it out right here. Let's say s is equal to 1 t, and then we have the next one is t squared. So these are the basis vectors in the polynomial space denoted by p to the power 2. The idea is that we can use these basis vectors to create any polynomial in that particular space. And here is one such polynomial created using those vectors shown here in red. We can look at the basis vectors as well. The basis vector the y is equal to 1, which is simply that horizontal line parallel to x-axis, which is just this 1. The next one is 3 times uh, x, which is that line right there. And here we are denoting that's the t part. Of course, the coefficients that we see 3, 5, those have to be calculated, and we'll see how. The next one is the quadratic part with the square term, and you see that that's the curved dotted line, which we are saying that that's the t square. And so the linear combination in this case would have been a0 times 1 plus a1 times t plus a2 times t squared, and that will get us the polynomial p of t. And we already have the values for this. So a1 we said that was 1, this we said this was 3, and we said that this was I think 5, and this then gives us the polynomial, which is 1 times 1 plus 3 times t plus 5 times t squared. So that's the polynomial if we are able to reach or create using these set of basis vectors above, and we are showing that right here. Now, as I said earlier, the basis vectors can be anything. The only key is that they need to be independent, linearly independent, and the number of basis vectors in that set has to be minimum that can represent that space. So we are in 2D polynomial space, so we need these 3 items right here. If we use a different set of basis vectors, let's say we use s is equal to, we still have the 1 as you see here, but this time we are going to use something else. So that's the blue, which is going to overlap because that's the same polynomial we're trying to create. That's the y is equal to, wonder why we have the animation playing. So we just have that y a is equal to 1, so that's That's the one. Then we have this line, and then we have this line. So this is going to be 1 plus t, and then we have 1 plus t squared. So that's the what t plus 1 or 1 plus t, and uh, x squared plus 1. So that's 1 plus t squared that we have written here. And so the polynomial that we create with this is simply going to be a0 times 1 plus a1 times 1 plus t plus a2 times 1 plus t squared. And so the general idea here is that the values or that we have for these are as follows. So that's we have x plus 1. Okay, so that's the general polynomial equation we have, and I think the values for a. So the key idea here is to think about these basis vectors as if I were to give an analogy, this could be thought of as Lego blocks. And let's say we have this is the that we are going to use to build the entire house, right? And so let's say that this is the red block, or this is the blue block, and this is the green one. And so the idea then to create any polynomial is how many of these red do we need, how many of these blue do we need, and how many of these green ones do we need. So that's the sort of the story behind it. If we have a different set of basis vectors, of course, then that will change uh, how many of the red, blues, and green blocks you need to build that entire house. For example, if I just say that uh, uh, we have a polynomial which looks like this. So p of t is equal to 2 plus 39t plus 241 t squared. So completely random. And then what we would say that we can build even this particular polynomial that we just wrote down here using these basis vectors. How? By combining the values. So we could say that to get to 239 to 41, we essentially need two blocks of red that we have. So we have this one 100, then we need 39 blocks of blue, and so it's a 0 1 0, and then we need 241 blocks of the green, which is written here by 0 0 1. And when we combine this, of course we would get the vector right here. So this is nothing but 2 0 0. Then we have 0 39 0, and then we have 0 0 241. That's essentially 239 241, which is written right here. So that's the combination we would have to use to create this particular polynomial that we have. And so if you are asking, well, what is a in here and what is t, the a's are these values which we have, a 39. So this is going to be our a0, this would be our a1, and this would be our a2. And this is the basis vector we have, which is uh, t is going to be 100, t2, sorry, that's the one that we have. This the red part is this one, the blue part is the second one, and the green part, the t square part, is the third one. Now if we have a tilted set that we have here on the right hand side, and to calculate the values of uh, the coefficients that we have here, which is a0, a1, and a2, we would do that as follows. we have the let's say we use a simple equation that we have used here, which is the p of t is equal to 1. uh, so here I've used 1. Let's say I think we are using 2, so let me correct that. This has to be 2 and not 1. So 2 plus 3t plus 5t squared, and that's based on the standard basis that we just looked at. Now in tilted basis, which is this one, we can write that as p of t is equal to a times 1, so that's a0 times 1 plus b times 1 plus t plus b, or just to keep things the same, I'm going to use a1 times 1 plus t plus a2 times 1 plus t squared, and that comes out to a0 plus a1 into a1 times t plus a2 plus a2 times t squared. And we can now combine these again so that the coefficients are sort of aligned. And we can write this as a0 plus, so this is, there has to be a plus sign here, a0 plus a1 plus a2, that's by itself, and then we have plus which is this term, which is a1 times t, and then we have this term which is a2 times t squared. And so as you can see that we can try and match that with the coefficients that we have above. So this term right here is for this two, this term is for this one, and this term is for this part right here. And so what we have is a0 plus, let's change the colors again, we have a0 plus a1 plus a2, that is equal to 2, and then we have a1 is equal to 3, and we have a2 is equal to 5. If we plug these two values in here, we can get the value for a0. So a0 is equal to a1 is 3 plus a2 is 5 is equal to 2, so that's 8. And so the value for a0 is 2 minus 8, that is minus 6. And thus our final coefficients then are these: minus 6, 3, and 5 for a0, a1, and a2, and we can then put that back in this equation. So the polynomial would have to be written as follows: minus 6 times 1 plus 2 times 1 plus t plus, or rather minus, right, plus 5 times 1 plus t squared. And this is the same, these coefficients that we have here, uh, right here, they would give us the same polynomial that we started out with, so to get this particular polynomial. And the idea then is that we were able to get this polynomial using these set of basis vectors and these set of basis vectors as well. The key difference was the values for coefficients. So with the standard basis coefficients, basis vectors, standard basis vectors, the basis coefficients were 2, 3, and 5, whereas in the tilted option that we just looked at, the coefficients were different, which was -6, 3, and 5. Now let's look at the plot, and here we see that that's the polynomial we are trying to create, and earlier we saw that these were the uh, sort of the basis vectors, polynomial basis vectors that along with those coefficients that had to be used to get to that polynomial in blue. Likewise, we can create the same polynomial with a different set of basis vectors, uh, which was t, as we saw earlier. That was what uh, 1 plus t and 1 plus t squared. That is shown here. This is x plus y, x squared. So imagine that x is just t, and so if we try and plot these now, these are the values, and that gets us this again the same polynomial that we have in blue. So that's the overlap there, and we can see that the dotted red line, that's at an angle, that's moved because we are having different coefficients this time, and likewise we have different coefficients. We have different lines shown here, dotted lines, where we show x plus 1, which is t plus 1, and t squared plus 1. So to avoid confusion, I'm just going to not show these lines in blue and just look at the blue, the red, and the black lines, which clearly show us that we can use the basis vectors uh, which are shown here by the dotted lines for the black and the dotted lines for the red, create our polynomial, which is shown here by the solid line in black. So in summary, here is what we need to remember is that when we are talking about spanning a space, what we are saying is how far our vectors can reach. How far our vectors when we reach when we either scale them or we add them together. So if we do that, then can we reach what points we can reach in space, and if we can reach every point in that space, if we can reach every point, then we can say that we so in that case we say that they span that particular space. The only criteria that we saw was that if in case of the basis vectors is that they need to be independent vectors, so they need to be independent, and if they are independent, they can be used as a basis vector to create any vector in that particular space. And then the standard there is the standard basis vectors, which are simply made up of ones and zeros, just as we saw earlier, and these can essentially reach any point in 2D space if we have this set of basis vectors. But it doesn't have to be ones and zeros. We can have different basis vectors. For example, we can have 1 1, or we could have 1 minus 1, or any other basis vectors to cover the same space that these cover. So the idea is that they need to be independent. Likewise, when we are talking about polynomial space, polynomial space, in that case as well, we need we can think about the basis vectors as these values right here, and again each of these can be thought of as a building block. So maybe some block like this, and then we have another block, and then we have maybe some other type of block, and then we are essentially combining these blocks to build our house in the end. And the what matters are the coefficients. Each coefficients are what matters. So each of these building blocks that we have, which is either this one or this one or this one, can create the house that we are looking for. The only difference is going to be each of these is going to have a completely different set of coefficients when we put them together. So that was it for this video, in which we build did build up upon our previous idea of linearly independent vectors, and here we saw how those independent vectors can be used as basis vectors to create new vectors in that space by either scaling or adding them together. If you have any questions, comments, or suggestions, please do let me know in the comment section below. I hope you learned something in this video. Please like, share, and subscribe. Thank you, and I hope to see you all in the next video. Bye for now.